chapter 4 about ergodicity. Let me maybe do a quick recap of overview of what we have been doing so far from the beginning of this course, just to show you the picture of this course. So remember, we always considering this our dynamical system. We have a sigma algebra, we have a measure mu, and this is a topological space. And in general, we suppose this map is measurable. So if you remember, what we have seen first was first chapter is Poincaré recurrence. So this tells you that mu f invariant. This implies that mu almost every x is recurrent to any positive measure set. Is recurrent to any positive measure set. Okay? And yeah, so think of mu invariant for certain maps like the circle rotation. You have Lebesgue is invariant. In general, if you have the determinant, if you have a diffeomorphism, the determinant being 1 is invariant. And in the next chapter, we have seen when we have the existence of invariant measures, okay? Like when you put some structure on your space, like if this is a compact metric space, you know, you can always have invariant measure, okay? And remember, we have seen in the next chapter, chapter 3, we have seen Birkhoff. That gives a refinement of Poincaré by saying that, you know, if you have mu f invariant, this will imply convergence of time averages, okay? Convergence of time averages. What is this? This is saying that if you have a potential, you evaluate this potential along the orbit, this is converging to a function for mu almost every x, and this function is measurable also. Okay? And this chapter that we are in, we have ergodicity that gives a refinement of these results. Ergodicity. It tells you that now this limit is constant, okay? So ergodicity, we have mu f invariant and ergodic. This implies that phi tilde equals constant mu almost everywhere. Okay, and examples of ergodic systems. Ergodic. We have seen the circle rotation is ergodic. We have seen also that if you have an expanding map, like the full branch map that we had, like KX mod 1 or the Gauss map, if you add bounded distortion, we discussed this distortion. Okay, bounded distortion is just a way to show that the derivatives are comparable, okay, along the orbit. So if you fix certain scale between the points, this implies that Lebesgue is ergodic. And in particular, we have seen that in particular ergodicity of any measure that is absolutely continuous with respect to Lebesgue. Okay? Ergodicity of mu absolutely continuous with respect to Lebesgue. Okay? Yes, because if you remember, like the full branch map that we were considering, like the Gauss map, it's not Lebesgue that is invariant, but you have another measure that is absolutely continuous with respect to Lebesgue, and you prove that it has boundary distortion, then you have absolute continuity. And for the, how to say it, for the Kx mod 1, you have Lebesgue that is invariant and is ergodic by this property. And also, if you remember last lecture, I was doing the Bernoulli shift. So if you remember, what we did was, you know, we have the space. Let me just simplify it to have 0, 1, and you have sigma to be 0, 1 to the power n, and you have sigma, so the shift map, just shifting from the left to the right. And we have seen that we have a measure that is defined here, and we also have that this guy is ergodic. And what was interesting about this dynamical system was that it is conjugate to, like, for instance, this specific one is conjugate to like to 2x mod 1. So you have this picture that if you have 0, 1, the interval to 0, 1, you had, let's say here we have our shift map, and there is a way, you know, to code elements here by using sequences, and you have this diagram commit. So this is 2x mod 1, so this is sigma, and this is a homomorphism. By the way, you know, this is minus certain, you know, you take out a countable set of points, okay? Because you take out the points in the boundaries of the partition, and they're pre-images. Yeah, so studying this dynamics is simple. If you don't care about differentiable structure, if you just stop at the level of continuity, like topological properties, like you're looking for dense orbit, you're looking for periodic orbits, you're looking for measures and stuff, you can, you know, translate the property from this guy to this one, because this one is easier to study, okay? At least when you have finite symbols, okay? And this scheme has like a more general version when you put here not only 2x mod 1, you know, any annals of like uniform hyperbolic system you have here, you can always find the symbolic dynamics with more symbols probably, so that you have this diagram, okay? So there are many studies in dynamical system that uses this diagram. The fact that you have your chaotic system here, you model it via symbolic dynamics, and you know, you translate everything from here to there, and yeah, via this. So you have sigma composed with h equals h composed with f. So you have this conjugation, okay? And last time I attempted to explain the Hopf argument, which proved ergodicity for general hyperbolic systems, but I realized that, I mean, for this course we don't have enough tools to do the whole Hopf argument, because it requires to have some knowledge about, you know, foliations, absolute continuity, and so on. And the example we were considering was this one, which is simple, the cat map 211 from the torus. And Lebesgue is invariant, and the way we proved that Lebesgue is ergodic was via, you know, I mean, Hopf argument. I just tell you quickly like how we did it. We have phi plus, we define phi plus to be the limit when n goes to infinity of 1 over n, the forward limit equals 0 to n minus 1 So this induces a map FA, okay? So when you induce the map, you use this matrix mode 1, I call it FA. So what you have is C compose Fi. So this is for this guy. Phi plus minus, so this is plus minus I. And the idea to prove ergodicity, it was reduced to prove that this is constant. This limit is constant. And the Hopf argument was to realize that, to observe that phi plus is constant along stable leaves. So we had this, let's say we had a stable eigenspace. So ES, stable eigenspace. This guy will be constant along stable eigenspace. We have seen that. So this is another stable eigenspace. And you have unstable eigenspace that is transversal like this. So Hopf tells you that phi plus is the same here. Okay, let's say this is ES1, this is ES2, two stable eigenspaces. So Hopf tells you that phi plus, I mean, using the hyperbolicity, phi plus, let's say you have here a point x, you have here a point x prime of x equals phi plus x prime. So this is Hopf. We have proved this last time because, when you go forward, the point x and x prime, they get nearby. Hopf. And from here, we see that this is phi minus of y prime, where y prime is this point. This is via using Birkhoff theorem, okay? So this is Birkhoff. I'm just recalling what we said last time. And you can see that this, by Hopf again, is of any, it is phi minus is the same, so, and this is again phi plus, if you want, of y prime. And you see that phi plus being constant, these two will be the same, so you basically prove that phi plus equals constant Lebesgue almost everywhere. Yeah, this is the Hopf argument. As I said, we don't have here the tools to do the general version. When you, in the linear case, you don't have problem because you have nice disintegration of the measure. Lebesgue measure is just the product of measure on the stable and measure on the unstable. But in the general setting, we don't have enough tools to do it here in this course. If someone is interested, it can be a topic for a presentation at the end. But for this course, we will not do it. So I will give you another proof for this type of systems, like ergodicity for this type of system. So we will do endomorphism of the torus. Okay, so you take a D by D matrix. So this is just a generalization of this example. You take a D by D matrix. So this matrix, if it lives invariant the lattice, so if this implies that this induces a map on, you can define a map on the torus, okay? TD, which is RD, ZD, okay? Because it lives invariant the lattice, so it gives this. So an exercise that I will ask you to check is that FA preserves Lebesgue. So it is conservative. So we will prove this theorem here, which is another way to prove ergodicity not using Hopf. FAM is ergodic if and only if A has no eigenvalue that is a root of unity, has no eigenvalue that is a root of unity. Okay, so this is, a generalization of this. Another way to prove Lebesgue is invariant, not using Hopf. But this method is, more general because it applies to nonlinear system. Okay, this picture it applies also to nonlinear system, under some conditions about the foliations. Okay, so let's prove this. Proof. So the proof is similar to the proof we did when we prove the circle rotation is ergodic. So, so suppose that you don't have a root of unity, you don't have eigenvalue. So suppose no eigenvalue is root of unity. Okay, that means that, so this means that if you have lambda in the spectrum of A, then lambda m is different from 1 for all m, okay, in Z, okay. Now to prove ergodicity, it's enough to prove that invariant functions are constant, okay. So let's take a function, so let C in L2 m. I mean, there's a reason to use L2 here because we have a nice basis of L2. L2m such that phi composed with Fa equals phi invariance. Okay. Now L2 having a countable basis, you have this basis of functions, so which is I'm on Rd, so this is exponential 2 pi I k x for k in Zd. So this is the usual inner product. So this is a vector on Rd on the torus, and this is a countable basis. Is a countable basis of L2. So what it means is that you can write phi as ck exponential of 2 pi I kx, okay, where here k is in Zd, is a vector integer entries. Okay, so this is of x. So now what is phi composed with fa x? So this is just an application of the matrix because, because you have 2 pi I, that makes it mod 1, okay? So because the other guy will be, ax and x mod 1, they have the same value, okay? Of ck. So this is the inner product. So sorry, I don't know what I'm doing here. So this is the inner product on at D, okay? So this is, so yeah, I think you understand what I'm saying here. Okay, AX and this of ck. This you can write it as a star k x. Okay. Now this is a basis. Being a basis, it means that if you write your function, so this is phi of x, which is this guy. So what this means that for every k, you have c a star k equals ck. Right? Yes. So phi composed with fa equals phi. This implies this. Actually, this is equivalent for all k in zd. This is similar to the proof we were doing for the circle rotation, okay? If you remember, we used the same techniques here. Now, so we want to prove that this function is constant. That means that we want to prove that these are zeros except for k equals 0, okay? So there's this claim that uses the hypothesis here is that this set for k different from 0, okay, 0 of zd, then this set is finite, a star k am star, sorry, a for n. This guy is infinite, like, okay? This guy is infinite. Why is this true? Because if not, you would stop. Okay. If not, you would be like this. Would be a closed orbit. If it is finite, it would be a closed orbit for this. So if not, you'll have there exists m such that a star. Okay, there exists m and l such that a star l plus m equals a star m. This for all l, okay? Yeah, you don't need to say this is for all m, and this would imply that you have eigenvalue that is a root of unity, okay? So this would imply that there exists lambda in the spectrum. So this guy is infinite. So if this guy is infinite, the only possibility for this to be true is that these are 0 except for k equals 0. So then ck equals 0 for all k in zd and k different from 0, okay? So in particular, you would have that this is constant. Almost everywhere because I'm on L2, okay? I use Lebesgue here. Okay, and conversely also, if you suppose that you have a root of unity, you can construct a function that is invariant but not constant. So conversely, if there exists lambda in the spectrum of A such that A of m equals lambda, then you can define phi k, phi of x so being 1 everywhere is FA invariant, but not constant, okay, because you put this constant to be 1. So this is another way to see ergodicity when you have this type of linear matrices, okay, these matrices, okay. Yeah, so but this is very limited because it uses a lot the structure that you have here, linear map. So it doesn't work if you don't have linear map. So let me write properties of ergodic measures. So today our lecture will be a little bit shorter because I have a meeting somewhere. So so let's see some properties of ergodic measure. So, I mean, so we have seen what ergodicity implies for the dynamical system. Like, it implies that when you have these conversions, the time average is converged to a constant. But a measure being ergodic, what condition it imposes to, to the measure. So let's see that. So we start with this lemma. So if you have two F invariant measures, if you suppose that mu is ergodic, and nu is absolutely continuous with respect to mu, then these two measures are the same. Then nu equals mu. This is kind of very strong, just looking at it like this. It sounds very strong, and because, just absolute continuity, I mean, and this condition. This is why we see the power of Birkhoff theorem, like this type of, at least unexpected results, to see that when you have two measures that are invariant, one is ergodic, another one is absolute continuity, you have equality. For instance, this lemma, so an observation or a remark from this lemma is that for the full branch expanding map that we were interested in, so for instance, for the Gauss map, you can see that Lebesgue is not invariant from this remark, from here. Lebesgue is not invariant. I mean, there are many other ways to see it, but just to tell you about how powerful this is. Because if Lebesgue, we remember that for the Gauss map, we know the invariant measure. It is absolutely continuous with respect to Lebesgue. And we know that Lebesgue is ergodic for the Gauss map because of, we have the boundary distortion implies Lebesgue ergodic. Okay? So if Lebesgue was invariant, it would tell you that these two measures are the same. So what is violated here for the Gauss map is that Lebesgue is not F invariant. Okay, because recall we have d mu equals, I think it was thus, or log 2, something like, to normalize dx. Let's just do dm. So you have mu absolutely continuous with respect to m, and know that boundary distortion bd plus expanding implies that Lebesgue is ergodic. So what is violated here is that Lebesgue is not invariant for this map. So yeah, so this is a way to say that if you have two different measures if you have two different measures, so with this property, so one has to be singular with respect to the other one. Like there is a positive measure set that has zero measure for the other measure. Okay. So let's see how to prove this. Proof of the lemma. Yeah, so we want to prove that these two measures are equal. So it's enough to prove that. So enough to prove that they agree on functions. So equals the integral of phi du nu for every c. Okay, so okay, and if you take this function, you can consider the time average. So so if you have 1 over n, I equals 0, n minus 1, phi composed with, I will give myself some space here. So both being invariants, so this converges to phi tilde x for both mu almost everywhere and nu almost everywhere. Okay. Okay, so both mu almost everywhere and also nu almost everywhere. Okay. But there's no relation between the two sets. So mu being ergodic imply that phi tilde of x equals the integral of phi d mu. Okay, ergodic tells you that for mu almost every x. Okay, and what I wrote over there is that nu f invariant, this implies that phi tilde exists nu almost everywhere. Okay, just invariant. So this is just Birkhoff. And this measure being absolute continuous with respect to mu, so this will imply that this is constant, okay? Mu almost everywhere. Nu almost every x. So in this imply that these two integrals are the same. I mean, you have Birkhoff that tells you that the integral of phi tilde d nu, I mean, the integral of phi d nu, this is Birkhoff, okay? And this, by this argument above, this is the integral of phi d mu. Okay, so this is one properties of ergodic measures. So another remark, so see that the space of probability measure is convex, okay? So the space, we have seen this, I'm just recalling, because when we were proving existence, we prove that it is convex. We check that it is convex. I mean, there's nothing to do actually. the space of probability measures is convex. Meaning that if you have two measures, two probability measures, so you have mu1, mu2 probability measures, so in t in 0, 1, you have t mu1 plus 1 minus mu2 is also probability measure. So there is this proposition now, because this is a convex set. A question might be, where are the ergodic measures located in this set? Okay, where are these ergodic measures in this set? So we have this proposition that tells us that the ergodic measures are like vertices of this set. The proposition. So an invariant measure mu is ergodic if and only if mu equals t mu1 plus 1 minus t mu2 for mu1, mu2, m1. This implies that t equals 0 or 1. So this is to say that the invariant ergodic measures are on the vertex of this set. They are vertices of M1, the space of probability measures. Okay, so let's prove this. So suppose that the measure is not ergodic. We will see that we can write it as a convex combination where t is not 0 nor 1. Suppose that mu is not ergodic. So what does this mean? This means that there exists a set E such that f minus 1 of E equals E, and mu of E is in 0, 1, okay? It's strictly in 0, 1. Okay? So now you can define these two measures, mu1 of E. Okay, let's put here A, okay? Because E was like a generic measurable set, okay? So this is a set which makes ergodicity fail, like, so this is a particular set, so E is generic. So when we are defining a measure mu1, which is mu of E intersect with A, like the conditional measure, okay? This is the conditional measure on A. And mu2, mu of E intersect with A complement over mu of A complement. These are two probability measures, okay? Because this guy gives 1 to the whole, so on. So see that mu can be written as mu of A, mu1 plus mu of A complement mu2, okay? Like any set you take, any E, you can write this, because if you put here E, you have this and this will cancel out, and also and so on. So, and you have that this is exactly inside 0, 1. It's not 0 nor 1 because of what we say in this guy. So I mean, this is 1 minus this one. Okay, so 40 minutes. Okay. So there is so we see that ergodic measures are on the vertex of ergodic and invariant. Oh, the other way. I did not. Did I? No, I need to. Yeah. I did not prove the reverse. So conversely, sorry, that's just one way. So conversely, suppose that you have mu that is t mu1 plus 1 minus t mu2. Suppose that mu1 is different from mu2 and t is in 0, 1. So mu of E equals 0 because none of these is 0. So this would imply that mu1 of E equals mu2 of E equals 0. Okay, because these are just numbers, non-zero numbers. Okay, so sum of positive number is 0, so each of them has to be 0. Okay, and so this implies that mu1 is absolutely continuous with respect to mu. So this implies that mu1 is absolutely continuous with respect to mu, and also mu2 is absolutely continuous with respect to mu. So this is just the definition. This is just the definition of absolute continuity. So here you use the lemma that, so if mu was ergodic, so what you would have is mu equals mu1 by the lemma we have. So mu ergodic implies by the previous lemma that mu1 equals mu, which you don't have because we suppose we have this, which this you don't have. So similarly, here also this would imply that mu 2 equals mu. Yep. Yeah, so this is the end of the proof, that the ergodic measure, they are on the vertex of the measures that are invariant, the probability measures that are invariant, okay? So I want to close with a property that I was saying in one lecture that some people, they consider this as like ergodicity, like having a dense orbit, like transitivity. Because if you remember, I explained ergodicity as irreducibility, okay? Ergodicity. So as irreducibility. Meaning that you cannot decompose. So this is A complement. Non-ergodic means that you have a decomposition. And these both have positive measures. So ergodicity tells you that you cannot make this decomposition in a measure theoretic sense. Okay? But see that here, if you have a dense orbit, like if the system is transitive, what we call transitive is having a dense orbit. If you have a point that goes everywhere, it goes, start here, go here, like it is transitive. you would think that your system would be ergodic, like if you have a dense orbit. Okay, so one might think that ergodicity is like transitivity, like having a dense orbit, but that's not the case. That's not right. That's not a correct way to think of ergodicity. At least, I mean, mathematically, because there are examples. There are examples, and in mathematics, if we just have a counterexample, we rule out everything, even though some people might think that that example is just, you know, particular, very particular, but mathematically, ergodicity is not like transitive in a topological sense, like having a dense orbit. But we will see, I will write in a minute a proposition that tells you that ergodicity, you can think it as transitivity, but when you restrict to the support of the measure, like transitive in a measure theoretic sense. So measure. Theoretic sense. Okay. Because when you just say transitivity, it means that transitive, okay, mean that there exists x naught such that this guy is dense f in x naught n greater than 1. This guy is a whole space. So this is just topological. Okay, but there is a measure theoretic way to define transitivity using the support of the measure now, because here everything we're doing is with respect to a measure, okay? But if you know, you are thinking of physical system, like some real life system that your vision is only limited to Lebesgue measure. When you talk about Lebesgue measure, transitive in a Lebesgue sense might be close to transitive in the topological sense, because the support, you know, will contain open set in the support of the Lebesgue measure, okay? Contain open sets. So let me define what is the support. I have been saying it without defining it. What is the support of a measure? So in general, transitive doesn't imply ergodicity, not ergodicity imply transitive. So let's define the support of a measure. So given a probability measure, mu, so this is the support of mu, like we know from topology the support of a function. So this is the set of point P on your space such that mu of B, P, epsilon is positive for all epsilon positive. So this is an epsilon ball. So I'm supposing that I have a metric space here, okay? So this is an epsilon ball around P. Yeah, so see that the Lebesgue measure, for instance, is kind of fully supported. Lebesgue measure. When you say the Lebesgue measure is fully, a measure is fully supported when the support is the whole space. Okay, so Lebesgue measure is fully supported because it gives positive measure because it's defined using, you know, these open sets. So mu is fully supported if support of mu is x. So Lebesgue measure is fully supported because the measure of balls is positive. But so example, Lebesgue is fully supported. And if you have a Dirac delta, delta P, what is the support of a Dirac delta? So delta P is a measure that gives 1 if P is in E, in 0 otherwise. What is the support of this measure? Okay. Is? Exact, yeah. Yeah. Actually, that's why it's called an atomic measure. So this is just P. Because any other point, at least, I mean, I'm not on a crazy topological space. That points, I can separate them, okay? Like, if I take another point, I can separate it from P. That's a reasonable assumption on your topological space, okay? So these are called like atomic measures. These are measures. For instance, if you remember very well, with this dynamical system, F gives 1 over x. We have that delta 0 was the only invariant measure, okay? It's the only invariant measure. And it is an atomic measure. Usually these are not like the measure we are looking at. Okay, usually we are looking for measures that are fully supported, okay? And yeah, this is a measure that is ergodic, okay? But it doesn't see, I mean, it's not, this example is not a good example because this measure really for this dynamics is what the measure that makes sense. But if you take x gives 2x mod 1, you take a periodic points of period 2. So if you take delta equals delta half P plus delta f of P, where P is periodic, okay, period 2. This measure is also supported on this orbit. So the support of delta is this orbit P f of P. So I'm supporting that this is a periodic. So f square of P equals P. So this measure is invariant. And it is ergodic. But it's not a meaningful measure for this system because it doesn't see what is happening here. Like the set of points where you can apply Birkhoff for this measure is just these 2 points. And those 2 points, they are not really the general case. They are not what makes sense, like the point that you care about for this dynamics. So that's why usually people, they go to define physical measures, for instance. Maybe we'll talk about that later. These are the measures for which the set of points where you apply Birkhoff has positive Lebesgue measure. the set of points where you apply Birkhoff like this. So you can look at the back of this. For this example, Lebesgue is 0 for that set. It has 0. Lebesgue of that is 0 for this example. But if this is positive, now you have like a physical measure, a measure that sees a lot of your dynamics. Okay. Anyway, so this was just a remark. So the support is something important in dynamic systems, the support of a measure, because we are looking at properties in a measure theoretic sense. But if I'm not very clever, I can just think of, Lebesgue maybe, or something that looks like Lebesgue. It makes sense to look for measures for which the support is the whole space. Okay, it gives, like, the way to think about the measures, it gives positive measure set to balls. Anyway, so let me come back to what I wanted to write before I will just close in a bit. Proposition. So there is a lot of study toward these physical measures, like their existence, uniqueness, like ergodic measure, invent ergodic measure that is physical measure, okay? There are a lot of studies on this direction. So suppose that mu is F invariant. I always have my dynamical system. I need to put a condition on my space. M is a bare space, a bare space with a countable basis. I will tell you what it means, bare space with countable basis. Bare space, it just means that if you take countable intersection of dense set is also dense, okay? Countable, you can, because this is a proposition, actually I have not proved here, you can check it in the book, because I really want to. If mu is ergodic, then there exists a dense orbit in the support of the measure. Like this is just to say that F restricted to the support of mu. This will be invariant. Why? Why is this invariant, by the way? Why, if you take a point on the support, the image is also on the support? Because of this, you can see because of invariance. So this is transitive. Okay, having ergodicity, it means that the support is, like the dynamics restricted to the support is transitive, like there is a dense orbit. And so the reverse, having a dense orbit doesn't imply that Lebesgue is ergodic, okay? Because you might think so. There's an example. For this. I have about 3 or 4 exercises that I want to tell you to look at. They are all from the book before I close, because I have a Skype call in about 10 minutes. So today we will close earlier because we are finishing this chapter. Actually, it's a good time to 4.3.2. Yeah, so I would just maybe tell you to look at this in the book because I don't have enough time to write them. Exercises 4.3. You can check this with Mateos on Friday. 0.7 and 4.3.8. These are exercises that you can check in the book to just to consolidate what we are talking about here. So you see, throughout this course, what we have been doing is, trying to put more structure on the measure and proving more dynamical properties. Okay, so for the next chapter, what we will do is like an ergodic decomposition. Like if you have an invariant measure, how can you decompose it into ergodic like pieces? Like you have your space. So you decompose this space into pieces where you have a measure that is ergodic there. You have a measure that is invariant. You define measure mu p restricted to this element that is ergodic. So this is a short chapter. Maybe in one lecture we will just prove I will just prove the existence, and then we will do more properties. Like we will go to mixing of these measures after this chapter, which is another property, like a statistical property, that is stronger than ergodicity, and that implies more like statistical, more properties about informations about orbits of points. So I will stop here for today, and I will see you on Wednesday.